We've had a chance to look at some of the issues involved in binary operations, and now we're going to see how binary operations work on Zn, in particular addition and multiplication. So we're going to introduce what addition and multiplication looks like as binary operations on Zn. We're going to discuss some of the issues we addressed in defining them. And finally, we're going to look at some issues that we face when proving that the addition and multiplication that we define are actually well defined. So we know how addition and multiplication work in the integers. Each one is a binary operation on the integers. And our experience with the operations means that we are comfortable doing those computations with addition and multiplication. So how do we use that to define addition and multiplication on Zn? Well, again, must be binary operations. So we have two inputs that are congruence classes and one output which is also a congruence class. Each congruence class contains integers. Nice thing we know about integers is we know how addition and multiplication work. So we can use addition and multiplication of integers as part of our definitions of those operations on Zn. So here's what's going to be happening in the in-class activities. So you're going to go ahead and define addition and multiplication for Zn. We're going to do it a little bit differently than we did it in the last class. The elements of Zn, they are congruence classes, and that means they are sets of integers. Now, rather than write them at the normal way that we write congruence classes, we're going to make them actually look a little bit more like sets. So when we say S and T are in Zn, that S and T are sets. And we're used to seeing sets represented by capital letters, so maybe that'll make them look a little more set-like. That means each of those sets, S and T, are subsets of the integers. So if we want to identify S or T or the congruence class S plus T or the congruence class S times T, all we have to do is find an integer from each one. One of our big theorems that we had is each integer is in precisely one of the equivalence classes. So as long as we find one integer in the equivalence class, that enables us to define the entire equivalence class. So if we choose an element of S, that uniquely identifies S. If we choose any element of T, it doesn't matter which one, it uniquely identifies T. And if we want to identify S plus T, well, this shouldn't be surprising. It is a congruence class. We just have to find one integer in it. Once we find one integer in it, we know exactly what S plus T is. And that will uniquely identify S plus T, just like the other congruence classes. And similarly, if we want to identify S times T, find one integer that's in it, and that will uniquely identify the equivalence class S times T as well. And so whatever rules we set for computing S plus T and S times T, we got to make sure that those choices that we make with S and T do not lead to different outputs. The big danger that we have with defining a binary operation is we got to make sure that every way that we can do that rule legitimately always gives us the same results. All right, so now I think you're primed to work on the activities. The name of the PDF file is called Addition and Multiplication in Zn.